This is the lecture for the summer for AP Chemistry to go over the first three chapters in the textbook. Once again, a reminder that if you have any questions to let me know via email and also to get your textbook when you can so you can start going over this material if you are confused on anything. You'll notice on the first slide here I've shown the pages in the book that I'm referencing when talking about this. But one of the things that our textbook talks about is the families of the periodic table. Remember, you have this staircase that starts with aluminum down. Everything to the left, excluding hydrogen, is a metal. Everything to the right is a non-metal. Main group elements are referring to those in the s and the p orbitals. If you recall from Chem 1, we have S, P, D, and F electrons, the D being the middle, the F being the bottom. The main group, again, is the S and the P. Transition elements would be the D and the F. Alkali metals, very reactive metals due to them having only one valence electron. That is this first column of the periodic table, once again excluding hydrogen, which is a nonmetal, although it has one valence electron. Alkaline earth metals is the second column of the periodic table. Notice in green, we have what's called the metalloids. That staircase, starting below boron and aluminum, will have elements above and below metal or non-metal that these green ones have behaviors a little bit like metals, a little bit like non-metals. There is no real family name for other columns in the periodic table with the exception of the halogens, which is the fluorine on down column. These are the most reactive nonmetals due to having 7 valence electrons. They just have to gain one more to be at the octet. Speaking of the octet, noble gases. Helium on down. Technically, helium does not get an octet because it only fills its outer shell with 2 electrons. It's of a duet. However, a full valence shell of electrons is stability. That octet rule is something that we definitely talked about in Chem 1. So once again, these 2 pages in the book, we're dealing with the families of the periodic table. If we move on to mole conversions, this is something that is in your summer packet. I also included a little practice with significant digits. We do have to report our answers to the correct number of sig digs in AP Chemistry, and there's additional rules to sig digs that we'll be learning this year as well, so it's important that we remember the old ones. The example problem I've given here is how many atoms is 14.7 grams of copper. The periodic table that you have in your packet should be familiar to you. It's the same periodic table that you had in Chem 1. On unit tests for AP Chemistry, I'll be giving you the same periodic table that you will be given on the AP exam itself. That periodic table only reports to the 100th place. So that's why I consistently report to the 100th place when I do my mole conversion. Remember how this setup works is here's what I'm given. On the top of the conversion is what I want to solve for, 1 mole. On the bottom, my units have to cancel out, grams on the bottom, grams on the top. Periodic table tells me 1 mole of copper is 63.55 grams. If I do that step, these 2 grams cancel out, leaving me with moles of copper. My second conversion is using Avogadro's number, 6.02 times 10 to the 23rd. That's how many atoms are in 1 mole. Now, some of the conversions that you might see on that packet also have compounds in it, so then you simply have to add up the mass of the entire thing. But Avogadro's number is still what you would be using. Here's the answer I get when I'm done. Reason why I report with 3 significant digits is my first conversion has 3 sig digs. At the very bottom of this page is an important thing that I always mention to AP students as they're working on things. Really, the hardest part about AP Chemistry is not what we learn, but knowing what calculation to do and when. And what I tell students is whenever you're in doubt on what math you should be doing, you convert to moles. If you're giving grams, convert to moles. If you're giving volume of a gas, convert to moles. Again, we'll be going over a lot of different mole conversions this first unit. This one is a review, and hopefully, again, a little bit of practice with the summer packet will help out as well. Next thing to go over, which is on pages 89 and 90, is the two main bond types. Now in Chem 1, we went over three bond types. We went over ionic, covalent, and metallic. We will review metallic a little bit when we get to the third unit of AP Chemistry. I don't have it included here because our textbook doesn't have it included yet. Our textbook has it included with the intermolecular forces portion of our curriculum. But if you want a quick reminder of what metallic bonding is a whole bunch of metals stuck together by what's called a sea of electrons, or delocalized electrons, where the electrons simply bounce around between different nuclei, and all the nuclei's attraction towards these electrons is what holds them together. More common, we have to know about ionic and covalent. An ionic bond is due to a transfer of electrons. Notice in the sodium, it gives its one electron to chlorine. That way chlorine will have 8 electrons around it. Sodium will lose this one, so it'll go back one shell and also have 8 valence electrons. Right below the Lewis dot for sodium chloride, I've shown what ionic compounds look like when they are stuck together. So Na plus and Cl minus are held together in what's called a lattice structure, just a repeating unit of these different ions that are attracted to one another. So a couple different ways to represent ionic compounds. A covalent bond is due to a sharing of electrons. This occurs between nonmetals because in an ionic, a metal will give electrons to a nonmetal. In a covalent, you have two nonmetals, so both need to gain. They both can't gain, so they do the next best thing of sharing. Here's a good example of hydrogen fluoride or hydrofluoric acid if you've done your naming so far. Fluorine starts with 7, hydrogen starts with 1. When these orbitals overlap, these two electrons are in between the hydrogen nucleus and the fluorine nucleus. So fluorine's attracted to both of these, hydrogen's attracted to both of these. That is what a covalent bond is. However, we usually draw that covalent bond as a line. Here's the Lewis dot for water with 2 pairs of unbonded electrons and 2 bonded pairs as well. Again, our third unit of AP Chemistry goes into bonding in a lot more degree than what we've done before. Even things of why are we drawing water in this bent configuration will be brought up at that point as well. Next thing is something that we very briefly touched upon in Chem 1, talking about the different classification of matter. Chemistry is really the study of matter and energy. Now, energy would be its own separate little flow chart, but matter can be broken down into 2 categories. A pure substance, which means it's the same throughout. It's the same every time. You can't make it any different. There are 2 different types of pure substances. There is individual elements, like hydrogen gas, H2, zinc, Zn, sulfur, so elements. Compounds. Compounds can only be made one way. There's only one way to make water. It's H2O. Zinc sulfide is an ionic compound. So when there's only one way to do it, it's the same throughout every single time. It's a pure substance. Mixtures have a little more variety to them. We talked about homogeneous mixtures. Particular solutions we spent a fair amount of time on in Chem 1. But you could also have things like air, which is a mixture of different gases. You could have things like an alloy, like brass. Thing with a mixture, however, is it can be made differently. Heterogeneous mixtures is when you can see the different parts. So not only can be made differently, but you can see the different parts throughout. Things like a suspension where a solid settles to the bottom over time is an example of that. An emulsion where 2 liquids cannot mix, so you see the 2 layers like oil and water. Next brings us to naming of compounds. Again, this is in your packet. There are several pages on this, and some of the things that you will be seeing on the next slide is what is from your textbook as well. I know in particular students have struggled with my bottom 2 bullet points because not only in your naming review packet am I asking you to remember old types of naming, but I'm asking you to learn 2 new types of naming as well. So in this slide, I'd like to just go over with you the different types of naming. The first type of naming is what we'd call our simple ionic. Potassium oxide. Potassium's a metal, oxygen's a nonmetal. We make it end in "ide" to show that it's combining with something else. Potassium has a +1 charge as an ion. Oxygen has a -2 charge. In order for an ionic compound to be balanced, the charges must balance, which means we need 2 potassiums for every 1 oxygen. That's why the formula is K2O. Many of the transition metals, the metals from the middle of the periodic table, have more than 1 charge. And because of that, they need a Roman numeral to represent that charge. Chromium, for example, can be a +2 and a +3. There are even instances where chromium's a +6. This compound's called chromium-3 bromide. Well, if it's called chromium-3, that means chromium is a +3 charge. Bromine is a -1 charge. Again, perhaps you were taught cross and drop as a way to now take that 3 from chromium and make it the subscript for the next thing. The 1 from bromine is right here, although we don't actually write down 1s. But that's how you can get the formula CrBr3. Keep in mind, what I'm going over right now is if you're given the written name, how do you figure out the formula? You will also need to know how to go from formula to written name. This was something that we emphasized quite a bit in Chem 1. In AP Chemistry, there's not going to be a naming quiz or anything like that. It's all applications, material that you just need to be able to know. The next problem, iron 3 sulfate. If it ends in an 8 or an ite, you should be looking at your polyatomic ion sheet to see where this might fit in. So the polyatomic ion sheet was given to you. And a bit of news for you. That polyatomic ion sheet that I gave you that has an asterisk next to some things and says memorize these, you do have to, in AP Chemistry, memorize those. So you will not be given a polyatomic ion sheet for any test that you take from me or the AP exam itself. Sulfate is the SO4 polyatomic ion. It has a -2 charge. If it had a -2 charge, cross and drop would put the 2 behind the iron. Iron 3 means iron's a +3 charge. The 3 would go there. One type of naming that I don't believe I added onto the naming packet is hydrate naming. Recall, to hydrate yourself means to drink water. Well, a lot of ionic compounds are more stable in the hydrated format, where they are loosely bonded to water. Barium chloride hexahydrate, if I were to give a formula for that, I would first figure out what's the formula for barium chloride. Well, barium's a +2, chlorine's a -1. That's where BaCl2 comes in. This dot represents the loose bond between the ionic compound and the water. How many waters? Hexa is the prefix for 6. That is one of your covalent prefixes at the bottom of your polyatomic ion sheet, which once again you will have to know. Speaking of those prefixes, they are often used for covalent nomenclature. For example, N2O is a problem that you are going to be dealing with Lewis dot structures and how tricky it is and how rules of Lewis dot are a little bit more complicated than what you learned in Chem 1. But to name N2O would be dinitrogen, because there's 2 nitrogens, and monoxide. There's your 1 oxygen. The mono prefix doesn't have to be used. It could be called dinitrogen oxide, is also commonly done. But if there's more than 1, you do have to use the prefix. And again, if we're given the written name, the prefix tells you how many of each there is. That brings us to this bullet point on naming acids. There are 3 different types of acids that you have to be able to name. The first involves hydrogen and an element. One of the most common acids that you worked with in Chem 1 was hydrochloric acid, HCl. The example I'm giving you here, H2S, is hydrosulfuric acid. To name an acid that's only hydrogen with an element, it's hydro, the name of that element, ic acid. Notice I have 2 hydrogens here because sulfur is typically a -2 charge, so we need 2 hydrogens to balance that out. Now, if it's not hydrogen and an element, like hydrosulfuric acid, it's going to contain a polyatomic ion. here is H2SO4. This is an acid that you worked with in Chem 1. Notice the SO4 is the sulfate polyatomic ion. If it's a polyatomic ion that ends in 8, it's an ic acid, sulfuric acid. On the other hand, SO3 is the sulfite polyatomic ion. Little trick to remember this is the 8 polyatomic ion always has one more oxygen than the ite polyatomic ion. If SO3 is the sulfite polyatomic ion, an ite ion is an us acid, sulfurous acid. What you want to be able to do in any type of naming problem is if you see it starting with hydrogen, you need bells to be going off in your head saying, hey, this is an acid, I need to use my acid naming. The last type of new naming that I'm asking you to learn in that packet is for hydrocarbons. Now this isn't quite as important as the acid naming, but hydrocarbons are very common in 2 instances. One, combustion reactions. Propane is what you'd put in a grill to have it, if it was liquid propane, to have it grill your food. The second way that hydrocarbons are important is they are typically nonpolar substances, and nonpolar solvents are important for us to know. The way I know that this C3H8 is propane is on your polyatomic ion sheet on the very bottom, I hand wrote the first few prefixes for organic naming, and prop is the prefix for 3. If it ends in ane, that means it's all single bonded. So I have 3 carbons single bonded to each other, and then hydrogens would fill in the rest of the molecule, which would mean there's 8 hydrogens there. Again, I'm not going to do much in the way of hydrocarbon naming, but it is on your packet for you to be familiar with. And like I said before, the acid naming is probably the one that's a little bit more important. Your textbook has this flow chart. Is it an ionic compound? How do I name it? Only one type of ion, or it could have more than one. I need a Roman numeral. Molecular compound refers to a covalent compound. Covalent compound, prefix, name of first element, prefix, name of second element, end in -ide. Acids. Binary means 2. So is it just hydrogen and the name of that element, acid? Or is it a polyatomic ion that contains oxygen? 8 polyatomic ions are ic acids. 8 polyatomic ions are us acids. So through these couple of slides now, hopefully you can finish that packet if you haven't already. Recall that on Moodle is an answer key to this as well, and you can always email me if you have questions. Percent composition is something that we covered towards the end of the first semester in Chem 1. There's a couple of ways that you can perform percent composition. I'm going to show you the way that we did it in class, and I'm going to show you kind of the way that our textbook shows it, which again is on these pages. So the question I'm going to show you how to answer is determine the mass of oxygen in a 7.2 gram sample of aluminum sulfate. In Chem 1, if we gave you a problem like this, if you want to know the mass of oxygen in this sample, we would first figure out how many oxygens are in this compound. Its formula is Al2SO4 3. 3 times 4 means I have 12 oxygens. So what I did to find the numerator in my calculation right here is I took 12 times 16 to give me 192. The mass of the part divided by the total mass, which is referred to as the molar mass, so 2 aluminums, 3 sulfurs, and 12 oxygens is 342.17. That tells me that in this aluminum sulfate compound, 56.1% of it is oxygen. If then the question says, I have a 7.2 gram sample, how much grams of that is oxygen? I take my percent, I make it back into a decimal version, however, and multiply it by 7.2 grams to get my final answer of 4.04 grams. Perhaps with the 2 sig digs here, I should have called it 4.0 grams of oxygen instead. So this top bullet point is how we did percent composition in Chem 1. If you were to look at these 4 pages, 109 through 113 in our textbook, they would follow almost more of a stoichiometry method, where the first step would be to convert the grams of aluminum sulfate to moles of aluminum sulfate. Remember, when in doubt, convert to moles. So here's 7.2 grams. 1 mole over the molar mass gives me this many moles of aluminum sulfate. Again, perhaps I should have gotten rid of this 0 right here, only carry 2 digits. Although you'll find when I do a multiple step process, I usually carry 1 extra digit until the final answer. Secondly, if this is how many moles of aluminum sulfate I have, there are 12 oxygens in the formula for every 1 aluminum sulfate. It's almost like I'm doing stoichiometry within one compound. I'm looking for the ratio of oxygen, there's 12 of them, for aluminum sulfate, there's 1 of them. So that converts me into moles of oxygen. And then from there, I can multiply by the grams per mole for oxygen, which is 16. Gets me the exact same answer as how we did it in Chem 1. The bottom version that I just went over is a little bit more stoichiometry based. Either version is acceptable. That being said, me going over this review material with you is trying to remind you of things that we went over that are not a major point of emphasis. If it is a major point of emphasis, we will be going over it when we start class in September. These are things for you to be aware of, though, because College Board deems percent composition something that you should know about. Something that we did not get to last year in Chem 1, but perhaps we did the year ago before. This is usually the topic that if we have snow days, we lose during the first semester. If we don't have snow days, we teach during the first semester in Chem 1. It's called empirical formula. Empirical formula is really doing the exact opposite of percent composition. For percent composition, you're trying to find the percent of an element or different elements within one compound. In an empirical formula problem, you're given the percentages and you're trying to figure out the formula. So here's a question. Determine the molecular formula for the compound with a molar mass of 60.10 grams per mole and the following percent compositions. Here's your carbon, hydrogen, and nitrogen. In bold, I've given the directions on how we teach Chem 1 students to solve something like this. First off, if these are all percentages, let's just assume that they're grams. Because if it was a 100 gram sample, 39.97% of 100 grams would be 39.97 grams. So if I have a mass of each element, when in doubt, convert to moles. So notice my 3 mole conversions here for the different molar masses. That gives me a value for each of these. An empirical formula is the lowest ratio of moles to moles for each element in a compound. This needs to be a whole number ratio. Calling a formula C 3.33, H 13.3, N 3.33 would not be a good formula. But what I do is I divide by the smallest number of moles. So long as I divide each of these values by the same thing, it's not going to change the ratio. This gives me a 1 to 4 to 1 ratio. C1, H4, N1. And if I looked at that compound, that'd have a molar mass of 30.06 grams per mole. Looks to me that the molar mass in this compound is twice as large, so I doubled everything. C2, H8, N2. Again, empirical formula is another topic that is not of high emphasis for us, but it is something to be aware of. The last slide is dealing with chemical equations. In order to do stoichiometry, which is what we will be doing week 2 of AP Chemistry, we have to be able to balance chemical equations. Up on this slide, I've shown you the 5 main reaction types that we went over in Chem 1. I've written them all out, and I have not balanced them yet. So I want to remind you of how to balance chemical equations. Again, writing chemical equations is something we have to be able to do. Synthesis reaction is where you make one product. This is actually how to make rust. Iron plus oxygen makes Fe2O3. What I would notice is I have 1 iron on this side of the equation and 2 irons here. I have 2 oxygens here, I have 3 oxygens there. To balance a chemical equation, you put a coefficient in front. I would put a big 2 right where my cursor is. The reason why I'm doing that is now I have 6 oxygens on the reactant side. I'm sorry, the product side. If I put a 3 right here, that would balance that equation. Remember, if there's a 2 here, that'd give me 4 irons here. I'd put a 4 there. That would complete that synthesis reaction. Decomposition reaction is the exact opposite of a synthesis reaction. You start with one reactant and you make more than one product. Hydrogen peroxide decomposes into water and oxygen. If I put a 2 in front of my water, I can then put a 2 in front of my hydrogen peroxide, and this equation would be balanced. Single displacement. Metal, more reactive than the metal it's trying to replace within a compound, they switch places. Zinc switches with silver. It could be a non-metal switching with a non-metal. We did a halogen lab in Chem 1 to show that. Zinc nitrate's the new compound. Notice how I had to rebalance this ionic formula. I just didn't call it ZnNO3. When you make the switch, you have to make sure charges balance. And zinc is a +2 charge. Nitrate is a -1 charge. Therefore, I had to put the 2 here. With that 2 nitrates, that means I have to put a big 2 in front of silver nitrate reactant. And then I have to put a 2 in front of the silver product as well. Double displacement reactions occur when you have 2 ionic solutions. The strontium and the lithium will switch places. One of these 2 compounds has to be a precipitate, or something that isn't aqueous, because you could make a pure gas or a pure liquid as well in a neutralization reaction. You do not have to know quite yet how to determine that, but in Chem 1 we gave you a table of solubilities that told you will this occur or not. Similar to in a single displacement reaction, we gave you the activity series, a ranking system of which one was more reactive. Neither of those bits of information will be given to you on any test, but we will teach you some shortcut ways to identify whether or not a reaction that's a displacement, either single or double, will occur. Strontium switches with lithium. Lithium now with chlorine. Lithium's a +1, chlorine's a -1. That's why it's LiCl. Strontium's a +2, phosphate's a -3. That gives me this formula here. To balance this out, I would notice I have 3 strontiums here. I'd put a 3 in front of the strontium chloride. I have 2 phosphates here. I would put a 2 in front of this. By the way, it looks like I made a mistake. Lithium phosphate should actually be Li3PO4. So if this was a 3 then, I'd need a 6 there and everything would be balanced. So again, this formula right here, it looks like was incorrectly written. It should be Li3PO4. Last type of reaction is a combustion reaction. A hydrocarbon, a carbon-hydrogen compound, of which you were asked to learn the naming for. This is methane. This is what comes out of our natural gas jets. Plus oxygen makes carbon dioxide and water. 4 hydrogens here. I'd put a 2 right here to give me 4 hydrogens. That gives me 4 oxygens. I'd put a 2 there, and that would be balanced as well. So once again, this has been the review lecture on pages in our textbook that we will not specifically be covering day 1. This is material that I'm hoping that you are already aware of, so we can build upon it from there. If you have any questions, again, please feel free to contact me.